Okay, so the same rules as we've been looking at, the ones that you have to know. Only thing I might point out is over here, you've got if you lose electrons, you become positive because you lost a negative, and if you gain electrons, you've gained the negatives, you become negative. So 2 extra rules added on there. And remember, everything's based around that atoms want to have a full outer shell and be like the noble gases, which is group 0 on the periodic table, where they already have full shells. And that will explain why we don't have any compounds with helium and neon in. Okay, you love the title. Today's title, ionic bonding, just like we got to at the end of the last lesson. And where we got to was the fact that this atom here has lost an electron. This atom here has gained an electron, so that's a negative charge moving. That means overall this first one now becomes positive, and this second one becomes negative ion, and the two ions do not fall in love with each other. But we do say they are attracted to each other, and that's called an ionic bond. So, what's this? We'll get into that. Okay, 4 questions. You write out the question, you write the answer next to it, and then you unpause. Okay, let's see what you've put. What is the charge of an electron? They are negative. What is the charge of a proton? They are positive. If an atom loses 2 electrons, so it's losing 2 of the negatives, it'll be +2, positive by 2. And what type of elements bond in ionic bonding? It is always something from the left-hand side of the table, periodic table. It's a metal, and something from the right-hand side, so something that wants to lose electrons and to become positive, and something from the other side, the non-metal, becoming negative. Hopefully you got most of those right, and if not, you've made your corrections. So, just recapping, here we have 1 on the outside shell, and here we have chlorine with 7, and this one, when it reacts, sodium and chlorine react together, sodium will then have a full shell, and chlorine will have that extra 1, so it will have a full shell. They've both got 8. The sodium becomes positive, the chlorine becomes negative, and they attract together. Exactly the same in the example that you did last lesson, magnesium and oxygen. The positive magnesiums, the negative oxygens attracting together to form a solid magnesium oxide. So what happens next? Right, not many diagrams on this slide. Here is my positive sodium or iron or copper or any other metal I want to name, whatever I have reacted. Let's stick with sodium and chlorine. So let's stick with the sodium becoming positive and the chlorine becoming negative. There's a sodium, it's positive, and there's a chlorine, it's negative, and they attract together. We've said that, and that's called an electrostatic or ionic attraction. Right. The thing is, you've got millions of these and millions of these reacting together. So actually, this will also attract chlorine atoms in those directions. And the chlorines will attract the positive sodium ions in all directions. And when do I stop? Well, the answer is draw all day, but also make it 3-dimensional. So draw some behind it, so there's a positive going in there and there's a positive in front. And all of a sudden it will become very messy, and I find it difficult to draw in 3 dimensions. It forms a giant molecule. Now, what is a molecule? Molecules are just more than one atom. more than one atom. So you can say, oh, I've got a molecule of water, or I've got a molecule of oxygen. A molecule of oxygen has two oxygens together, hence O2. There's a molecule of oxygen, or there. But anyway, come away from that for a minute. This keeps growing into a massive, giant molecule. It's in a regular pattern. And that pattern of all these rows and grids of positive and negative ions is called a crystal lattice. So, in your notes, just explain that this attraction is in all directions. There's the first thing, number one. Number two, because of that, it forms giant molecules following a regular pattern, and that pattern, that structure, is a crystal lattice structure. And remember, this whole topic is called structures and bonding. So what we're dealing with here is, we're dealing with today's title, this positive and negative ions attracting. So ionic attractions in all directions leading to giant molecules with a regular pattern and a crystal lattice. That is a 6-marker answer to explain why. Why is sodium chloride solid? Oh, I know. It's because it has ionic bonds, which are strong attractions in all directions, forming giant molecules with a regular pattern, forming something called a crystal lattice structure. Oh, why does sodium chloride have a high melting point? Oh, I know. It's the same answer. And it's the same for every single ionic solid. Here's a drawing that I did earlier. Obviously I did it myself freehand. Exactly the same, the sodium and chlorines. So this is just showing what one layer would look like in that crystal structure. However, this, and you saw my attempt to draw a 3-dimensional shape, not quite as good as this, but there are, every single one of them is an Na+, and every single one of those green ones is a Cl-. Chlorine is a bigger atom than sodium. If you remember, it started with 11 protons here and 17 there. That has a total mass of 23, and this has a mass of 35.5 on average because of the isotopes, negative and positive, all held together. And as we've just said, all held together by strong electrostatic attractions, which we call ionic bonds. And there's a different diagram. So this is in reality. And these crystals, we found them in caves and in mines and stuff. You can find these crystals hundreds of meters long. That would be billions and trillions and trillions and trillions of atoms in that structure. So this is that crystal structure, and inside there, just like that diagram we just had, we'd have billions of atoms all in a crystal structure. Hence why crystals are made. And some of you probably as little children's had crystal making kits and crystal growing kits. You can make crystals with some really salty water and some thread and let the water evaporate away, and crystals will form on the thread. In fact, if at home you take some really hot water, as in don't burn yourself, and you put that into a cup, I suggest you try this because you're at home, most of you. Well, all of you are at home at some point, I'd hope. You haven't left home yet. Put some water in there that's really, really salty, as in you've put so much salt in it you can't possibly get any more dissolved. And then put a stick across the top or a pencil and hang some thread on it into the solution. And there's so much salt in there in that hot water. And now just leave it. Leave it for a few days. And as the water evaporates away, all the dissolved sodium chloride will start to form crystals on the thread. But try it and see. So, this is a key slide, putting together those key ideas. So every time you react a metal which becomes positive and a non-metal that becomes negative, every time you have ionic bonding, we have strong electrostatic bonds in all directions. It forms a structure called a giant crystal lattice, and those bonds are incredibly hard to break. It takes lots of energy to break them, and that's why they have high melting points and boiling points, and they are solids. So I would have that, the key properties of ionic bonding and ionic structures, in a nice clear box, highlighted. Make sure it stands out in your notes so you know that in future that's a key bit. So, in summary, looking at what you've just written, ionic bonding, all about gaining a full outer shell, rule number 9. They transfer electrons, so either they're giving them to another atom or they receive them. One sort of further complication, what I'd like you to do is try these two questions yourself first. So, how does magnesium and fluorine bond? So what I want you to do is, in a minute you'll pause. First of all, draw them. Draw magnesium with its 24, with its 12 electrons. Draw a fluorine with its 9 electrons. And see how they match up. What do they need to do? What does this one need to lose? What does that one need to gain? How's that going to work? Can you solve that problem? And then the second thing, once you've done that, what would the formula be of magnesium fluoride? So once they have reacted, what will the formula be? Okay, draw them, have a look at it, ponder it, see if you can work out what you think the answer is before you go on from this point. And here's the answer. So what would I have expected you to do? I would have expected you to be able to draw this. And you would have realised, magnesium needs to lose 2 electrons. Then what I would have expected you to do is I would have expected you to draw a fluorine and realise fluorine needs to gain 1 electron. And then the bit that might have happened in your brains, you might have gone, I need to lose 2. So there's one of them, there's the other. That means fluorine only needs to gain 1, so I need 2 fluorines. I need 1 up here to gain 1 and 1 here to gain 1. So there's my electron and there's my other electron. You can look at the red arrows or these blue ones hand drawn by me, much better. And then what you end up with is you end up with a magnesium ion over here with a 2 plus, and you end up with 2 fluorines. So the answer to question 1 then was this whole top section diagram drawn like this, and then here's your final product. And the answer to question 2 is MgF2, and that's how we come up with formulas. Magnesium will join with 2 fluorines, so the formula of magnesium fluoride is MgF2. Right, if you manage to work that out for yourself, brilliant, because now you're not going to forget it. If you got part way and then got stuck and needed help, that's fine. And if you just know it now from me going through it, well, I suppose that's also fine. But It's not the easiest. Make sure it's clear in your notes. Okay. 2 comprehension questions. Lithium and fluorine forming lithium fluoride, and potassium and oxygen forming potassium oxide. It's going to take you 10 to 12 minutes to draw those out properly and work out formulas. That would be great to see in the work that you submit by taking a photo and handing it in. Okay, obviously pause and do that, and when you're ready you can enjoy another chemistry joke. Thank you.